Hi, in this video we are going to talk about heaps, focusing on the removal operation. So let's get started. Basically, we have been already discussed how to insert items and how to construct a heap data structure. In this case, we are going to consider how to delete an item. So we just get rid of the item we would like to delete. Okay, but there will be a hole in the tree. So we put the last item there and make sure the heap properties are valid with the help of reconstructions, for example. So, for example, we would like to get rid of the root node, the 210. Okay, we just get rid of it, but there's going to be a hole. It's not okay, so we have to insert the last item there. So, the 5 is going to be the new root node. It's very easy to find the last item because in the one-dimensional array, it's going to have the index last index. So, it's quite easy to find it. Okay, it is a valid heap in the sense that it is complete, but we have to make sure that other heap properties are not violated. In this case, because this is a maximum heap, the heap properties are violated because the maximum item, which is the 100, is not in the root node. So, we just have to swap them. Okay, and after the swap operation, it's going to be a valid maximum heap, because here the parent is 100, all the children are smaller than the parent. If we are considering this subtree, then the parent is 5, the left child is 2, so the parent is greater again. So, it is a valid heap. So we have managed to get rid of the root node and to make some reconstructions in order to end up with a valid heap again. So what about the operation running time? Deleting the root node is going to take order 1 constant time complexity, plus we have to reconstruct the given heap, which is going to take logarithmic running time. Okay, so the overall running time will be logarithmic. And what about removing an arbitrary item? Okay, we have been discussing that if we would like to remove the maximum in a maximum heap or the minimum item in a minimum heap, it's going to have logarithmic running time because we know that the first item is going to be the root node in the array. But if we would like to get rid of an arbitrary item, for example, the user would like to remove the item with the value 23. Of course, first we have to find it in the heap data structure. What does it mean? That in the array representation, we have to iterate through on a sequential basis. So we have to consider every single item on a one-by-one basis. So basically, we are going to end up with a linear search. So that's why removing an arbitrary node is going to have ordo n running time, because first we have to find it. Okay, it's going to take linear time complexity, and we have to reconstruct the heap data structure. It's going to be quite fast. It will have logarithmic running time, but a linear running time plus logarithmic running time is going to be linear running time. So it's very important that, okay, if we would like to get rid of the root node, it's going to have logarithmic running time. But if we would like to get rid of an arbitrary item, because we have to find that given item, the running time is going to reduce to ordo n linear running time, which is not that good. But basically, we usually don't implement removing an arbitrary item from a heap data structure. Usually, the remove operation is going to get rid of the root node no matter what. This is why heaps have came to be. This is the purpose for this data structure, because we know that the maximum or the minimum item is at the root node, and usually we would like to get rid of the maximum or the minimum item. So that's why removing the root node is going to have logarithmic running time. Removing an arbitrary item, an arbitrary node in a heap data structure is going to have linear running time because we have to make a linear search in the one-dimensional array in which we store the items. So that's all about removal operation in a heap data structure. Thanks for watching.